Very good morning dear students, welcome to Tungal online classes. In previous class we have discussed the concept of electrostatic potential difference, and we have also derived the expression for electrostatic potential due to point charge and the relation between electrostatic potential and electric field. Yes, in today's class we shall derive the expression for potential due to an electric dipole, and we shall discuss the concept of equipotential surface and the properties of equipotential surface and electric potential due to system of charges. Yes. So let us start with the derivation of potential due to an electric dipole. As we know, electric dipole is a system of two equal and opposite charges which are placed at a certain distance. So in this figure, this AB represents the electric dipole with the magnitudes of the charges of plus q and minus q placed at points capital B and capital A respectively. Yes. So at B I have the charge of plus q, and at A I have the charge of minus q magnitude, and the distance between these two charges, that is the dipole length, so that we shall take it as a 2a. Yes, and let O is the midpoint of this electric dipole, so that the distance between the charges minus q and midpoint is A, and the distance between the charge plus q and the midpoint is A again. So this point O, that is midpoint of the electric dipole, will act as the reference point. All the distances we will consider with respect to this midpoint O here. Okay, and let us consider a point P which is randomly placed where we wish to calculate the electrostatic potential due to these two charges or the electric dipole AB. Okay. So let this point P be placed at the distance of R from midpoint of the electric dipole, and let R1 is the distance of this point P from minus q charge, and R2 is the distance of this point P from charge plus q. Okay. So I will repeat again, the point P is at the distance of R from midpoint of the electric dipole, and this point P is at the distance of R1 from minus q charge which is placed at A, and the point P is at the distance of R2 from plus q charge that is placed at B here. Okay. And we know by the principle of superposition the electrostatic potential at point P, let me call it as a V here. So this electrostatic potential is equal to the sum of the electrostatic potential because of this minus q charge and the electrostatic potential at point P because of this plus q charge. Okay. So let me consider the electrostatic potential at P because of charge minus q. Let me write it as a VA. Yes. Similarly, the electrostatic potential at point P because of this plus q charge, let me write this as a VB. And we know the electrostatic potential at any point due to a source charge, that is generally given by V is equal to 1 divided by 4 pi epsilon naught into the magnitude of the source charge, that is q here, divided by the distance between the point of configuration and the position of the source charge. Okay. So here I can write it as generally we write it as R. So this is the basic expression for electrostatic potential at any point P with respect to source charge because of this source charge. Okay. So when I consider the electrostatic potential at point P because of this minus q charge, we also know that the electrostatic potential is positive if the source charge is positive, and it is negative if the source charge is negative. So the electrostatic potential depends on what is the polarity of the source charge. So in this case we can clearly see here this charge the charge at A, that is minus q, hence I can write VA is equal to 1 divided by 4 pi epsilon naught. So this will be minus because the source charge is also negative. I can write it as minus of 1 by 4 pi epsilon naught q into, okay. So q divided by what is the distance between the point of configuration P and this source charge, that is nothing but R1, okay, plus. So at point B I have the positive charge, so the electrostatic potential at point P because of this positive source charge will be positive. So here VB will be plus here. So clearly here I can write it as 1 divided by 4 pi epsilon naught. The magnitude of this charge is Q and the distance between the source charge and the point of configuration P, that is nothing but R2. Okay. So this I can simplify it as 1 by 4 pi epsilon naught is common for both here and Q is also common. Inside bracket I can write 1 by R2. First let me write R2 here because it is positive, minus of. So here I can write 1 divided by R1. Let this be equation number 1. This is from basic expression of electrostatic potential. Okay. So let me call this as equation number 1. Yes. So then let us consider the line joining point P and the midpoint of the dipole. Let it make an angle of theta with respect to axis of the dipole. Okay, observe here. So the line joining the point P of configuration and the midpoint of the electric dipole, let it make an angle of theta with respect to the axis of the dipole. Okay. Then, and this I am showing it by the dotted line. So here let us consider some geometrical configurations. So from basic mathematics we know that whenever I have two lines, see here. So let me have some two lines, two long lines here. Yes. So when they make very small angle of theta between both each other, let theta is the very small angle between these two lines. Let me name the lines here. So let this be A to B and let it be C here. Okay. So when I have two lines which are very close to each other or which are making very small angle between each other, if I draw one perpendicular line from smaller line to larger line. So let me call this as point M. Okay. So if this angle AMO, if it is 90 degrees and the angle between these two lines is very small, in that case I can easily write AB is equal to I can write it as MB. Okay. So the condition is what? So there should be 90 degree angle between these two lines, that is AM and B to M. So in that case I can write AB is equal to MB. Okay. So here also to consider this, what I am doing here, I am just extending this dotted line. So whatever I have P to O line, so I am extending up to M, so that this line A to M is perpendicular to MP. Okay, I repeat again here. So I am extending the line P to O until point M, so that the line joining A and M is perpendicular to this dotted line. So here these two lines, which are these two lines, that is A to P and M to P, both are similar to these two lines. Observe here. So the lines A to P and M to P. So even though there is so much, this figure is exaggerated. So what happens here? Actually what we do, we consider the point P at very large distance from this midpoint, such that this R is much greater than A. So the distance between this A to O, which I write it as A, that is very small compared to the distance R. This point P is at very large distance compared to the distance of A. Okay. But for understanding, I am just exaggerating the figure. We are feeling as if this R is the distance A is significant compared to R, but when I consider R much greater than A, we can neglect the distance of A with respect to R. Okay, that we have to keep in mind, that point P is at very large distance from midpoint O. Okay, so the angle between these two lines will be very small. So by comparing these two lines with these two lines, I can simply write here, see here, I can write it as A to P is almost equal to what? So this perpendicular line is up to M, I can write it as M to P. Okay. So, these two lines AP and MP, they are making very small angle, and this angle AMO is 90 degrees. So, I can write AP is equal to what? MP. Okay. So, this is the basic consideration. Okay. So, AP is equal to what? MP, and then look, MP is equal to what? MP, can I write it as, observe here, can I write MP is equal to what? I can write it as M to O plus O to P. Okay. So, I am writing MP in terms of R. Okay. So, MP is equal to what? MO plus of OP. Okay. Then consider the right angle triangle AMO. Consider right angle triangle AMO. This is the angle here. This is my hypotenuse side, and the side opposite to this angle is what? Opposite side. This MO, is it not adjacent side here? So, consider from triangle I can write, from triangle AMO, from triangle AMO I can write MO divided by, that is adjacent side, divided by hypotenuse. What I am doing here? I am writing MO in terms of A. Final expression I want it in the form of R and A, and whatever these unknown terms are there, those unknown terms I am trying to write them in the form of known terms. So, here I have R. So, I introduced R here. OP is nothing but R. Similarly, I am writing OM in the form of A. So, what I will do here? From right angle triangle AMO, I will consider this side. This is adjacent side divided by hypotenuse, that is MO divided by AO. What is that? So, that is adjacent side divided by hypotenuse, that is nothing but cos theta. Is it not? So, from this I can write MO is equal to what? MO is equal to AO into cos theta. But what is AO? AO is nothing but half of the dipole length, that is equal to what? A into cos theta. So, I can write MO is equal to A into cos theta. So, substitute this in this equation. So, that is AP equal to, I can write AP is equal to what? What is MO? That is A cos theta plus of, what is OP? O to P is nothing but, that is the distance R. So, AP I can write it as, AP is nothing but what? So, that is R1 is equal to R plus of A cos theta. Let this be equation number 2. Okay. So, this is equation number 2 here. Okay. Similarly, now let us consider the second distance R2. Okay. So, let us take the distance of B to P. So, here when I consider two lines, again I will take pair of two lines. Which two lines I have to take? I have to take B to P and O to P here. So, we can clearly observe here, this O to P line is already larger. So, what I will do? I will just draw one perpendicular line. I am drawing one perpendicular line up to this dotted line here, so that this angle ONB is 90 degrees. Okay. So, now I consider these two lines, that is B to P I will take and N to P I will take. So, these two are also making very small angle between each other, and there is perpendicular line from one point to another line. So, I can clearly write, see here, from geometrical configuration I can write BP is equal to what? NP. Why? Because these two lines are making very small angle between each other, and this line BN is perpendicular to NP. So, from the similar geometrical consideration I can write again, that is BP is equal to what? BP is equal to, I can write it as NP. Okay. So, I am writing BP is equal to what? NP here. Again observe here, I will write this unknown term in the form of R and in the form of theta. Okay. So, again consider, already I have BP is already in the form of R2 here. So, this NP I will write in the form of R and theta. Okay. So, for that what I will do? Observe this O to P here, observe the line O to P, right. So, from this I can write NP, that is NP is equal to what? NP is equal to OP minus of ON, right. So, what I will do here, so LHS I have already BP here, BP is equal to this NP is nothing but OP minus of ON, right. So, I write it as NP is equal to what? O to P minus of ON, minus of ON. Again, consider the right angle triangle ONB here. Again, I will take the right angle triangle of ONB. From this, I will take, this is again adjacent side, right. So, from the similar consideration, I can write cos theta. So, this is my angle, this is the adjacent side and this is the hypotenuse. I can write cos theta is equal to what? ON divided by hypotenuse is OB, okay. ON divided by OB. So, this implies ON is equal to what? That is equal to OB cos theta, is it not? ON is equal to OB cos theta. I can write it as ON is equal to what? So, that is OB is nothing but O to B is, that is half of the dipole length A into cos theta, okay. So, that is A into cos theta. So, I will substitute this ON here. So, I can write BP is equal to OP minus of ON is nothing but A cos theta, okay. So, then consider what is BP here. BP is nothing but R2, yes. BP is nothing but R2 is equal to OP is nothing but R minus of A cos theta. So, I got the expression in terms of R and theta, right. So, here I can write R2 is equal to R minus of A cos theta. Let this be equation number 3. Okay. So, now what I can do here. So, consider equation number 1. In equation number 1, I have 1 by 4 pi epsilon naught Q inside bracket 1 minus of R2 minus of 1 minus of R1. So, here I substitute R2 from equation number 3, that is R minus of A cos theta, and R1 I substitute from equation number 2, that is R1 is equal to what? R plus of A cos theta. Okay. So, that makes my derivation simple. So, what we shall do here? Let us replace this R1 and R2 by equation numbers 2 and 3 respectively. So, I will write this equation for electrostatic potential V again. So, that is equal to 1 divided by 4 pi epsilon naught, Q is common, inside bracket I will write it as, what is R2 here? R2 is that I can write it as 1 divided by R minus of A cos theta minus of what is R1? R1 I write it from equation number 2, that is 1 divided by, I can write it as R plus of A cos theta. Let us just simplify this. This I can take the LCM. I will write it as 1 by 4 pi epsilon naught, Q is common. I can write the LCM as this is in the form of A minus of B into A plus of B. This directly I will write it as 1 R square minus of A square cos square theta. Yes, can I write it like this? So, here I will get it R plus of A cos theta. In the numerator I will have R plus of A cos theta minus of I will write here, I will get R minus of A cos theta. Yes. So, let us simplify this. I can write this equation V as 1 by 4 pi epsilon naught, 1 divided by 4 pi epsilon naught into Q. So, in the denominator I have R square minus of A square cos square theta. So, look at this numerator here, this R and this minus R both get cancelled. I will have, and this minus into minus, it will be plus of A cos theta. So, I will be having A cos theta plus of A cos theta, that I can write it as 2 times of A cos theta. Okay. And you can take the screenshot of this so that I can erase this part. Yes. Let me erase this. Now, consider here, I can write V as, so we know in previous class we have electric dipole moment which is given by P is equal to Q into 2A, where Q is magnitude of the charges of the dipole and 2A is the dipole length. So here also I have Q here also I have 2A. So this Q into 2A I can simply write it as, this is 1 by 4 pi epsilon naught, Q into 2A I can write it as P into P cos theta, I can write P cos theta whole divided by, I can write it as R square minus of A square cos square theta. Okay. And this is the general expression for electric potential at a point due to an electric dipole. Yes. So here R is the distance of that point P from the midpoint of the electric dipole, A is half of the dipole length, and theta is angle between the line joining point P and the midpoint O with respect to axis of the dipole. Yes. So here we have different cases. See here, what happens when this point P is on the axial line? Yes. So if the point P is on or is along the axis of the dipole, in that case theta will be equal to what? 0 degrees. Yes. So let us consider the cases here. When P is on axial line, in this also we will be having two cases. If the point P is towards a positive charge, that is, if the point P is somewhere here, that is between midpoint and the positive charge, your angle will be equal to what? 0 degrees. Okay. The second case is, if the point P is between the midpoint of the dipole and the negative charge, in that case you have to measure angle from 0 degree, that will be 180 degrees. So here there are two cases here. In first case, when the point P is between a positive charge and the midpoint, so in that case theta will be equal to what? 0 degrees. Theta will be equal to 0 degrees, and I can write V is equal to what? V is equal to 1 by 4 pi epsilon naught. This cos theta will be equal to 1. Yes. So simply I can write it as P divided by R square minus of A square. Cos square theta will also be equal to 1. Yes. Similarly, if the point P is between the midpoint and the negative charge, in that case, so I will get theta is equal to what? 180 degrees. When theta is equal to 180 degrees, this cos theta will be equal to what? Minus of 1. So I can write V is equal to 1 by 4 pi epsilon naught P into cos theta will be equal to what? Minus of 1. So here cos square theta will be again equal to plus 1. Denominator does not change here, that is R square minus of A square I will have. So this I can write it as minus of 1 by 4 pi epsilon naught P divided by R square minus of A square. This is the general expression for electrostatic potential when the point P is between the midpoint of the electric dipole and negative charge of the electric dipole. And we have another case here, if the point P is on the equatorial line. Yes. So on the equatorial line, this angle will be equal to what? The angle between this line and the dipole axis will be equal to 90 degrees. Theta will be equal to what? 90 degrees. So cos theta will be equal to cos 90 degrees. Cos 90 degree will be equal to 0. So easily I can write V will be equal to 0. So this is when the point P is on the equatorial line. So I will have three cases here. One is when the point is between midpoint and the positive charge. Second case, that is when the point is between midpoint of the dipole and the negative charge. And the third case, that is when the point P is along the equatorial line. It can be either along positive y-axis or along negative y-axis. In both the cases, this angle will be 90 degree. So your electrostatic potential V will be equal to what? 0. Okay. And already initially I told the distance R, since this distance, if this distance is greater than A, what happens? R square will be much greater than A square. So I can easily neglect A square in comparison with R square. Okay. So in that case, and the maximum value of cos square theta is equal to what? 1. So I can simply write r square minus of a square cos square theta is nearly equal to r square. I can neglect this a square cos square theta. Okay. So, maximum value of a square cos square theta is equal to what? That is a square. Since r is much greater than a, r square will be much greater than a square. So, I can simply replace this denominator by r square. I can write this general expression as v is equal to 1 by 4 pi epsilon naught, that is p cos theta divided by r square. Okay. So, this is the expression for electrostatic potential when r is much greater than a, and in vector form I can write this expression as v is equal to 1 by 4 pi epsilon naught. I just replace this p cos theta by p into r cap divided by r square minus of a square cos square theta, where this r cap is the unit vector along the direction O to P, that is the line joining midpoint of the dipole and the point of configuration. Okay. So, this is the final expression for electrostatic potential at a point P due to electric dipole. Next, we shall discuss the concept of equipotential surface. In previous class, we have seen whenever I have some source charge, let me have source charge of plus q at any point P, the electrostatic potential because of this source charge, if the distance between these 2 points is r, the magnitude of the electrostatic potential at any point P is given by the equation V is equal to what? 1 divided by 4 pi epsilon naught q divided by r. Okay. What are the factors which affect the magnitude of this electrostatic potential? See, here 1 by 4 pi epsilon naught is constant. So, the electrostatic potential depends on the magnitude of this source charge. If your source charge magnitude is more, definitely electrostatic potential magnitude will also be more, and it is inversely proportional to the distance between the point of configuration and the source charge. If the distance is more, your electrostatic potential also reduces. Okay. So, what happens if your source charge is kept constant? Okay. If your source charge is kept constant, I can easily write V is inversely proportional to R, that is V just depends on the value of R, it is function of R. Okay. So, let us consider, for understanding this, let me consider some source charge of plus q. Okay. What we shall do, let me consider the points, which are at the same distance from this source charge. Let me place the source charge at the center of a circle. Let me consider different points. Let me take point A, point B, let me take another point C, let me take one more point D here. Okay. Such that all these distances are equal, that is equal to the radius of this circle. Okay. So, even when I consider this point A, the electrostatic potential at A, that I write it as VA. So, VA will be equal to what? VA is equal to 1 by 4 pi epsilon naught, the magnitude of the source charge, that is equal to what? Q divided by what is distance between this point and this source charge. So, that is R, is it not? Similarly, if I write the expression for electrostatic potential at B because of the source charge, so that is also same or not? Because the distance is same and the source charge is also same. So, I can simply write VA is equal to VP is equal to VC is equal to VD. If you consider n number of points, any number of points which are equidistant from the source charge, at every point the electrostatic potential will be same. What is the condition? All those points must be at the same distance from the source charge, and the magnitude of the source charge should remain same. Okay. In such conditions, what happens? The electrostatic potential is constant. In this case, I am just considering a circle which is 2-dimensional. It is just on the surface of this board, but this is not confined to only 2-dimensional surface. It is true for a 3-dimensional space also. What is meaning of that? See here, this point A, you did not draw it on the board. You can take it outside the board. You can take it in front here. Okay. But what is the condition? This distance must be R. You can consider anywhere. You can consider, if it is my source charge here, you can take point A here. You can take point A here. You can take point A here. You can take point A backside. Okay. you can place that point anywhere in 3-dimensional space. Okay. So, if you have huge number of points like that, if you join all those points, that will form a spherical surface. Okay. But what is the condition? All those points must be at the same distance of r from the source charge. Okay. This 3-dimensional surface, on which the electrostatic potential due to source charge is constant is called equipotential surface. What happens here? If it is my source charge, if you have all the points at the same distance, so we have clearly seen here the electrostatic potential is just function of the distance. If the distance is same, if you consider very large number of points like that, and if you join all the points, that will form a spherical surface. Yes, for this example, when my source charge is an isolated point charge, a spherical surface around that source charge has same electrostatic potential all over that surface because of the source charge. Such surface we call it as a equipotential surface. The name itself suggests that the potential on that surface is equal, that is constant. Okay. So, this is the example for a equipotential surface, and again we shall see here for the same source charge. Let me consider this is the source charge placed at the center. If I have one spherical surface around it, let radius of the spherical surface is r1. Yes, when the same source charge can have different equipotential surfaces. How it is possible? It is possible when I change the distance here. If I take another larger spherical surface whose radius is more, r2 is greater than r1, that is also possible, is it not? So, on this surface, so if the electrostatic potential on the first surface is V1, every point on this surface will have same electrostatic potential of V1. Yes, when I consider this is my surface 2, on the surface 2 my electrostatic potential due to the source charge will be equal to what? V2. Okay, the second surface is having same electrostatic potential of V2. Every point on this second surface that will have same electrostatic potential of V2. Again, I can take another spherical surface which is having radius of R3. So, I want to say that here a same source charge, the same source charge can have different equipotential surfaces depending on the distances of that surface with respect to the position of the source charge. Yes, this is one definition of equipotential surface. We can define equipotential surface in another way also. See here, this is my source charge plus Q. Yes, let us consider this is the spherical surface. Okay, let me consider 2 points. Let me take point A and let me take point B here, and we have already seen these distances are same. This distance is R, let this distance is also R. The electrostatic potential at A, let it be equal to what? VA. The electrostatic potential at B is equal to what? VB. Yes. So, what is electrostatic potential at VA? Is it not equal to VB? I can clearly write VA is equal to what? VA is equal to VB. So, when VA is equal to VB, the potential difference between these 2 points A and B is equal to what? If I write it as VAB is equal to what? VB minus of VA. Since both are equal to each other, I can clearly write the potential difference between these 2 points is equal to what? 0. If you consider another point, let me take point C here, VC is the electrostatic potential at point C. Again, the electrostatic potential difference between A and C is also equal to 0. The electrostatic potential between points B and C is also equal to 0. Okay. So, if you consider pair of any 2 points on the equipotential surface, the electrostatic potential difference will be equal to what? 0. Okay. So, this is another way of defining equipotential surface. I can say equipotential surface, it is a surface, yes, it is a surface on which any 2 points have the electrostatic potential difference 0. Yes, I repeat again, equipotential surface, it is a surface on which the electrostatic potential difference between any 2 points is equal to 0. This is also simple definition of equipotential surface. Yes. So, when my source charge is a isolated point charge, the equipotential surfaces will be in the shape of spherical surfaces. Okay. What happens if if I have uniform electric field like this, in such conditions what happens? Yes. So, I am showing the uniform electric field by the help of equally spaced parallel electric field lines. Okay. In such conditions, my equipotential surface will be plane surface, something like this. Okay. So, let me call this is surface number 1. So, let this be surface number 2. All over this surface number 1, the electrostatic potential, if I consider this is point A, this is point B, if this is point C here, at every point on the surface 1, the electrostatic potential will be same. Okay. So, this surface 1 and this surface 2. Surface 2, it is at certain distance from surface 1. So, when the distance is different, definitely the electrostatic potential because of this electric field. So, this is the uniform electric field. Because of this uniform electric field, on this surface we have some electrostatic potential V1. Okay. All over this first surface, our electrostatic potential will be equal to what? V1. Similarly, all over this surface 2, the electrostatic potential will be equal to what? V2. V1 will not be equal to V2 because both are at certain distance. Okay. But every point on this second surface will be having same electrostatic potential of V2. Every surface on this first surface, every point on this first surface will have electrostatic potential of V1. So, when we have uniform electric field, so this is how we have the equipotential surfaces, and this equipotential surface will be always perpendicular to the electric field lines. Okay. So, this is another condition. All these surfaces, you can consider any number of surfaces, all those surfaces will be always perpendicular to the electric field. Then only we can call them as electric field lines. Yes. Similarly, we have another two cases here. So, when we have electric dipole, how will be our equipotential surfaces? See here, we know the electric dipole will have two equal and opposite charges. Okay. So, it is pair of two equal and opposite charges separated by certain distance. If I draw the electric field lines between them, we know the electric field lines originate from positive charge and they will terminate at negative charge. So, this is how we have the electric field lines. Similarly, on the other side also we will have electric field lines which are starting from the positive charge and getting terminated at the negative charge. We can clearly observe here, in between these two charges the concentration of electric field lines is more, and as we move away the concentration of electric field lines, that is reducing or they are dilating. Okay. So, I will draw the same figure here. So, this is positive charge of plus Q, this is negative charge of minus Q. Here we have more concentration of the electric field lines. So, I will be having, if it is my first equipotential surface. Yes. So, as I move inwards, as I move towards the negative charge, the distance between these surfaces reduces. Okay. So, and as I move away, the distance increases here. The distance between equipotential surfaces increases. Yes. So, this is how I have the distribution of equipotential surfaces, and this will be due to second charge. Yes. So, I will be having a distribution of equipotential surfaces something like this. Yes. So, inwards the distances between equipotential surfaces decreasing, and as I move away from the source charges, the distance between equipotential surfaces, that is increasing. Okay. So, this is the figure for the distribution of equipotential surfaces when we have an electric dipole. Yes. Similarly, we have the last case of pair of like charges. Yes. So, when we have two like charges, those like charges either they can be positive charges or they can be negative charges. Okay, so let me consider plus q charge at A and plus q charge at B here. This is point of B, and for simplicity we shall take both magnitudes same. If I draw the electric field lines, we know these lines never intersect each other, right? So this is how the electric field lines will be distributed like this. Yes, so they never meet each other. So here also, since it is positive charge, I can show them outwards. So here also this is positive charge, I will show them outwards. So they will move away from each other, they repel away from each other. So this is the nature of distribution of electric field lines. Okay, we can clearly observe here, in between these two charges the number of electric field lines will be less. Okay, so as I move away from here, so here I will be having more concentration of electric field lines. So I can show the equipotential surfaces like this. So this is plus q charge, and here I have a plus q charge. The same figure I am repeating here, and my distribution of equipotential surfaces will be exactly opposite to that of a electric dipole. Yes, so here I will have, so if it is my first equipotential surface, outwards the distance goes on reducing. As I move inwards, the distance goes on increasing. Yes, the distance increases inwards and the distance decreases outwards. Yes, so this is how the equipotential surfaces are distributed. Inwards the distance is increasing and outwards the distance is decreasing. Yes, so I will be having some equipotential surface something like this for the pair of two like charges. Either they can be positive charges or they can be negative charges. If I have negative charges here, these electric field lines will be moving towards the source charges. Next we shall discuss the properties of equipotential surfaces. As we know, it is a surface on which the electrostatic potential difference between any 2 points is equal to 0. Yes, so first property, we can say that two equipotential surfaces never intersect each other. What is that? Two equipotential surfaces never intersect. As we know, the electrostatic potential V is given by what? 1 by 4 pi epsilon naught q divided by r. Let me consider an isolated point charge here. So if the magnitude of that point charge is q, let us consider certain distance r. The spherical surface around that source charge having a radius of r, so every point will be at the same distance of r. Okay, every point on that spherical surface will be having the same distance of r. If I have to consider another equipotential surface will be made up of n number of points which all are at the same distance of r2. So let me write this is r1. If I consider another equipotential surface, so this equipotential surface will be made up of huge number of points which are at the same distance of r2. Okay, when this distance is different, first surface is at the distance of r1, second surface is at the distance of r2. So when these two surfaces are two different distances, definitely they can never intersect each other. If I say these two surfaces are intersecting each other, those are not two different surfaces, that is only unique surface, that is only one unique surface. Okay, so this is by basic understanding of definition of electrostatic potential. We can state that two equipotential surfaces never intersect each other because every point on that surface must be at the same distance. Hence, two equipotential surfaces will never intersect each other. Yes. Then second property we can write as the work done to move a charge on to move a charge on equipotential surface, to move a charge on a equipotential surface is 0. Yes, why it is so? See here, in previous class we have studied, if this is my source charge of plus capital Q, let me say I am having some source charge of plus capital Q. So let me have a small charge of plus Q at point A. Let me consider another point of B. This is the direction of electric field. Okay. So if I want to move this test charge of magnitude plus Q from A to B, the work done is equal to what? So if the potential at A is equal to VA, if the potential at B is equal to what? VB, and there is some potential difference between these two positions, so that potential difference I write it as a VAB. VAB is the potential difference between the points A and B. And if I want to move a charge of magnitude plus Q from A to B, that work done is given by, work done is equal to what? The potential difference between them, which is nothing but VAB into magnitude of the charge which we are moving. If the magnitude is more, we have to do more work, is it not? So this work done is given by the potential difference between these 2 points and the magnitude of the charge. This is basic about electrostatic potential difference. But when I consider an equipotential surface, so let us say this is the source charge of plus Q. Okay, so this is point A and this is a point B. Let us write the potential at A because of the source charge is VA, and the potential at B because of source charge, let it be VB. Okay, and let me move some test charge of magnitude small plus Q from A to B. I am trying to move this charge from A to B. What is the work done here? Based on the same expression I can write VWD is equal to what? Work done to move the charge from A to B, that is equal to potential difference between A and B into magnitude of the charge which I am moving. Is it not? But what is the definition of equipotential surface? We have already stated it is a surface on which the electrostatic potential difference between any 2 points is equal to 0. That is the definition of equipotential surface. Hence, in this case, your potential difference will be equal to 0. Hence, the work done to move a charge between any 2 points on an equipotential surface will also be equal to 0. Okay. So, if there is any work done, if there is any work done that violates the definition of equipotential surface, hence there is no work done in moving a charge from one point to another point on an equipotential surface. That is the second property of the equipotential surface. Yes. The third property, that is the equipotential surface. The equipotential surface is always perpendicular to the electric field. Yes, it is always perpendicular to the electric field due to source charge. Here, so just I was explaining. So if you have some uniform electric field like this, I had shown the equipotential surface something like this. Okay, and this equipotential surface is perpendicular to the direction of electric field. Yes. So why it should be perpendicular to the electric field? See here, what happens? Let us consider the surface. If it is not perpendicular to the electric field, what happens? See here, let me say it is something oblique like this. Okay. If it is my electric field, let us consider the surface which is at some angle to the electric field. In such condition, what happens? If it is the magnitude of the electric field, so this electric field I can resolve into 2 components. Yes. So I will have some perpendicular component like this, another component will be along a surface. So this electric field, I am showing only example of one electric field line here. Let us assume I am considering it for a net electric field. This net electric field can be resolved along 2 components. One is along the surface parallel to the surface, another is perpendicular to the surface. Okay. So, here in this case the electric field is not constant, the electric field is changing with the distance. If I want to move some charge from position A to B, if I want to move some charge from A to B, because of the difference in this electric field intensity, the work done is not same. Yes, the electrostatic potential at A is different, the electrostatic B at B is different, because there is some net electric field intensity along the surface, there is some parallel component of this net electric field. Okay. Hence, we have to do some work to move the charge from one point to another point if the surface is not perpendicular to the electric field. So, in such case, I cannot call this surface as a equipotential surface. For any surface to be equipotential surface, it must be perpendicular to the direction of electric field. There should not be any horizontal component, there should not be any component along the surface of the given surface, yes, parallel to the given surface. So, to fulfill that condition, the given surface must be always perpendicular to the direction of electric field. So, equipotential surface is always perpendicular to electric field. If it is not perpendicular, there will be some component of electric field intensity parallel to the surface. So, in that condition, we have to do some work done. We have to do some work to move the charge from one point to another point on that surface, which violates the definition of equipotential surface. The last property is that positions of equipotential surfaces, the positions of equipotential surfaces depend on magnitude of electric field intensity. What is meaning of this? See here, if I have some source charge Q here, if I have some source charge of plus Q, so the equipotential surface will be distributed like this. Yes. So, for this, let us understand the relation between electric field and electric potential. We know electric field intensity is given by what? Minus of dV divided by dr. Okay. So, when I consider two surfaces, here the potential difference is V1, here the potential difference is V2. So, this is first equipotential surface and this is a second equipotential surface. If I consider any 2 points on these two surfaces, the potential difference delta V, that is dV, is a constant. Okay. When dV is constant, then simply I can write the magnitude of the electric field intensity is inversely proportional to the distance. What is this dr? Dr is the distance between the positions of these two equipotential surfaces. Okay. So, if your electric field intensity is more, the distance between the equipotential surfaces will be less, because electric field intensity is inversely proportional to distance. Hence, if your electric field is strong, the equipotential surfaces will be placed very close to each other. See here. So, let us say if my charge, let me call this as Q1. Let me consider another charge Q2 here. Let me consider another source charge Q2 such that Q2 is greater than Q1. If your source charge is stronger, so what happens? Your electric field is also stronger. So, let us consider this is the magnitude of the electric field E1. Similarly, if I have magnitude of electric field due to this source charge Q2 is E2. So, here the electric field intensity is stronger than this. So, in such condition, what happens? The equipotential surfaces will be placed very close to each other. When I compare these two cases, in second case the electric field intensity is stronger than the electric field intensity of first case. Hence, the distance between the equipotential surfaces will be less. Okay. So, that is what we are stating here. The positions of the equipotential surfaces depend on the magnitude of the electric field. So, this magnitude of the electric field again depends on what is the magnitude of the source charge. So, these are 4 important properties of equipotential surfaces.